Right, so today I'm going to try to talk about 301, remove invalid parentheses. Basically, we have a string input with parentheses and some non-parentheses characters, which we don't really care about in the end, I guess. So what the question asks us to do is to remove the minimum number of invalid parentheses to make the string valid, and we should return all the possible results. So just looking at the example here, we have an input string looking like this. We can remove the 1, 2, 3, 4, the fourth or the fifth character, which are both closing parentheses, to get the first valid string result, which is open closing open closing open closing. The other possible result here is obtained by remove the second character here. So this example tells us that for the same input string we can have multiple result. So it's true that it's a plural here. And I guess another thing is all the results in this results collection are going to be of the same length, because they are obtained by the same minimum number of removal. If one of the string is obtained by more number of removals, they will violate the definition. They are obtained with the same number of minimum removal. So they're going to be obtained with the same number of parentheses being removed from the original input string if they are all in the results collection. The second example here, in terms of the parentheses, they are exactly the same as the first example. They just have a non-parenthesis character mixed in there, and as a result, the result is actually the same. It just still have that non-parenthesis character in there. The third example, it's closing and opening parentheses. There's no way we can remove only one to make it valid. So as a result, we remove everything to go to the worst case from input string to empty string. So this tells us that in the worst case, we have to search for all the possibilities. So let's say we have m parentheses. Every character, every parenthesis has a option of being removed or not. We can potentially go to 2 to the power of n possible substrings to search for. So that's the worst case. So if we think about this question in terms of treating this substrings as nodes in a graph, and we're doing some kind of searching inside the graph, then there are only one kind of edges. It's outgoing edges, directed outgoing edges, and it's connecting a node of string, of course, to a node with a string that's length 1 minus. That's have one less character compared to the source substring, and that edge represents to one single removal of parenthesis operation. So that's pretty much the space we should search for. We are operating on, and we are given a root node to that graph. And if we treat all the substrings of the same length as on the same level, if we then can do a BFS search on this graph from the root node. Would be just consider all the possible substrings with the length L minus 1, then all the possible substrings with length L minus 2. That would be a breadth search. We can, if we do this, once we reach a valid string, the first one that we encounter, we know that it's the minimum number of removal we have been performed. And once we get there, we know all the results that we want are gonna be on the same level. So this leads us to very naturally to think about let's go for BFS search. It's not a horrible first attempt, so we're gonna code that up in the beginning. Just a a few quick notes before we go into the code. I guess the start to code this thing up. I guess one observation we can get from this example is that if we have a consecutive closing parenthesis or opening parenthesis of the same type, we can reach, at least based on this example, we can reach to the same nodes on the next level, the substring that's less one short. There are multiple ways, there are multiple edges that's connecting these two nodes. So there could be parallel edges, and we don't really care about how we reach there, which edge we pick. So we could use some mechanisms to reduce the redundancy in there. So that's just one quick observation by looking at this example here. So with that said, let's start code. Let's say that we're using a set to store the results, because there could be duplicates. If our implementation is not optimal or not, it contains certain redundancy in the code, in the logic, then we can use a set to deduplication. So it's not ideal, but it will be a reasonable first try. And we got the candidates, which represents to the current level of searching, which initially is the input string. I'm gonna try to code the main logic here. The while loop, it's gonna be level by level, and this is explore this level. We're gonna have a temporary set to collect the possible nodes in the next level, just to do a deduplication, so that when we do 4 nodes in the level, we are eliminating all the duplicates. And for every substring in the same level, what we're gonna do is to test whether it's valid or not. If it's a valid, we're gonna add it to the results collection. Otherwise, we will see, do we really need to go even further into the next level? We can tell that by just looking at the results. If it's not empty, meaning that this level is going to be the level, then we don't want to do any further exploration, so we don't push any next level nodes into this collection. Otherwise, we would do that. So since it's a set, it's an update here, and we will have some the valid here, and this get next will be some helper method we will code up shortly after this main logic part. So that's pretty much the level by level traversal BFS. And for each of the levels, we are testing the candidates, and if we have it, we push it onto the results. Otherwise, we will try to go from that candidate node and to follow all the possible edges we can follow to grab all the nodes in the next level, and just collect all of them into this set to do this deduplication, and then we set it to be the level that we want to explore in the next iteration. So just to quickly code up the helper method here. For determination of the valid parenthesis string, basically we do a linear scan from left to right. We keep track of the unclosed opening parenthesis, and whenever we see opening parentheses, we increment that counter. Whenever we see closing parentheses, we decrement that counter. When that counter goes below 0, meaning that we have closing parentheses that close nothing, we should then the string is invalid. And in the end, we should have the counter to be 0, meaning that all the opening parentheses has been successfully closed. So that's a linear path constant space code for checking whether the string is valid or not. For the characters in this candidate, we're gonna test if it's opening parentheses, we're gonna increment the counter. If it's a closing one, then we decrement the counter. We test whether the counts is less than 0. Do we have closing parentheses that has nothing to close? And in the end, we return we tested whether we closed all the opening parentheses. So that's the that's the method to test the validity of the candidate string. And then we have a helper to generate follow the edges to go to collect all the nodes in the next level that's associated with a node in this particular level. We check all the locations in the string. If the character is a non-parenthesis one, then we don't care. Otherwise, we will just construct a substring by eliminating one of the parentheses. So that's the helper to generate all the possible follow the edges of this node to grab the next level nodes that's associated with this node. We do the deduplication with this being a set. So that's pretty much the code. So you can see that in the first level we would this will be order of n, and if we exclude the time to construct a string, which we should because it's linear, then just think about this level we have n. Next level for n nodes, it's gonna search for n-1 possible candidates, and let's say that we have k minimum number of parentheses we need to removal. Just multiply those things out, we will end up with something like n to the power of k. So that's exponential in terms of the possible all the parentheses, all the length of the string in there. So in the worst case, it's looking like that exponential number in terms of time and as well as the space. So let's say if this code works, it should. Yeah, so the code works, and it's not too slow. It really brute force testing everything except use this set to do some deduplication can then be like 50% of the code there. So that's this first version of the BFS. Then what kind of duplicates we have in this code here? And one obvious one is that this get next here. So for all the candidate, it doesn't really care about which parentheses you got rid of in the first round. You try all the possible parentheses to get rid of this time. So let's say that you moved the zeros location in terms of the original string, and you get rid of the one string in the second iteration character location 1 character. In the second branch of the node in the first level, which is you obtained by get rid of the first character in the original input, the first branch for that particular leaf node will be getting rid of the zeros location character in the original string. So you're basically doing for I from 1 to n, 0 to n minus 1, and nested it with another 4 from j from 0 to n minus 1. So it's like a double counting. One thing we can definitely get rid of is this. So to have the second loop, nested loop, to only try the eliminations that's after the parent one, we could pass in a location in here. So instead of just the candidate substring, we also passing the last modified location in terms of the current candidate string here. So we changed the way that we are enumerating over the string. And for that to work, so the stuff on the levels here are gonna be a tuple with the candidate string as well as the last modified location. And so to unpack this, we'll grab both of this information. And the get next will need two pieces of information, both the candidate substring and also the last modified location. So this will eliminate the double counting before the set, but after the set, the reduction is not. I don't think it's halving the problem size. So we should get a little, very tiny little bit of. Speed up. That's from my guessing, I guess. So let's quickly check whether this quick small modification it's okay. Yeah, it looks okay. Let's see if it works. Okay, so what? My mouse. So it really isn't. So well, we could try to implement, try to find some other place we can do improvements, I guess. Okay, so let's look at a string here to see if there are obvious mistakes that we have here. Let's say that in the last iteration we removed the opening prefixes. For the next iteration, we don't want to remove the immediately closing prefixes after that last removal, because if we do that, we will the two consecutive removals, we just basically removed a valid prefixes in the string. That will cause us to even if we ended up in a valid string, it will cost us more than the minimum number of removals. So this is a quick check that we can put into this get next method here as well. So let's put that in there. So for that to work, we need to adding one more information here. In the beginning, the last removal is nothing. There's nothing being removed. It's empty. So we need to also unpack this last removal here and pass it into the link following method here. So if the last removal is the opening prefixes and the current character we are looking at is a closing prefixes, then we would want to skip. And I guess another one is if we have that's the very initial observations that we got from looking at the first example, is that if we have a consecutive prefixes of the same type, we don't need to do the edges basically are parallel, so all we need to do is just follow one of those. So let's add that logic in here as well. So if we are to the yeah. So this is saying that the previous location is the same character as this current one that we are looking at. Then because we already tried the follow the link there, we don't follow the link here. So these are the few additions that we did in there, and I think that yeah, let's try to submit this actually. Okay, we find an error. Oh, okay, the year here. We should year the last modified, last removed character, which in the case here is the one that we are removing. So it should work now. So yeah, we get a quite a huge jump in terms of the speed in time complexity. The reason is that this is pretty much the this is actually the case for duplication, right? This is this means the parallel edges inside the graph. And since that once we consolidated all the parallel edges, so the row for this set here it become you know not existing, because if we are not generating duplicated nodes on the levels, then there's no need for a set here. So yeah, we're gonna do a quick modification to eliminate the need for the set, because the set here the key is a tuple, right? And the first element in there is a length and string. I guess the hashing that can be you know, it's not as if we just directly put this onto an array. So I guess this will save a little bit of time in Siri. So let's do that. So we no longer need this thing here. Instead, we're gonna do like because we're doing BFS, let's use a queue. And since there are no queue in Python, we use deck. Just copy the theme thing here, and we should get rid of this. Also for because so for level wise, we just have a for loop with the number of nodes in the level instead of this this for loop here. Okay. And we can pop this information out from the deck. Pop from the left, so that we are doing BFS. And here the updates, it works for set but not for the deck here. So it's candidates.extend. And we don't need this anymore. Okay, so let's see. With this here, we pretty much consolidate with this here. We consolidated all the parallel edges, and hopefully we can have some speed ups. Okay. Yeah, let's try this. Okay. it works slightly faster. It could be random variable, random things. All right. So I guess one last thing we can do is to actually pre-calculate the for this BFS version is to pre-calculate the possible depths, the number of links we should follow in the sequence to get into the minimum number of removals, because that's actually something we can calculate. It's not so obvious to me in the beginning that when I reach this solution, I don't realize that, but when I read some of the solutions, I find this could potentially be a time-saving initial addition into my solution. So we can do very similar to this validation for the string to be valid or not. We can do a one pass through the string and just count the number of opening and closing parentheses we see, and just based on that information, or we try to decrement or increment the thing two counters, and we will be able to figure out exactly how many invalid opening parentheses and how many invalid closing parentheses are there in the string, so that for all these nodes here in the graph, we can actually use that additional information to help us to even trim the search tree, even prune the tree even further. Whether that can lead to some speed up, that's based on that depends on the test cases you have, I guess. But in theory, it should be able to help getting some speed ups. Let's say that we're gonna write a simple procedure similar to this valid here. I'll actually put it here. Okay, so initially we have left and right. We will use these two variables to indicate the number of unclosed open parentheses and dangling closing parentheses, extra closing parentheses. So we're just gonna do one pass through the string. If it's open, then we increment this counter for the opening parentheses. If it's a closing parentheses, then there are two things we need to do. If we do have an opening one, we decrement L. Otherwise, we'll increment R. So in the end, the variable L is the number of opening parentheses we need to remove, and R is the number of right parentheses, the closing parentheses that we need to remove. So with that, before we do anything, we actually grab those two values by scanning through the string once. And then in the get next, we can actually use this two information. So the logic is that if we already get rid of L number of opening parentheses, then the only one that we can get rid of to get to the next level, grab the nodes in the next level, is going to be those that we can go through a pass that by eliminating closing parentheses. So if we shouldn't remove left parentheses, and this character just so happened to be opening parentheses, we don't want to follow that edge. And here it will be if we follow the left link, if we remove left parentheses, we decrement this. It could be done by. Oh no, let me actually just convert this. So if we follow an edge of left parenthesis symbol, opening parenthesis symbol, we decrement this. If we follow the right one, we decrement R. That's pretty much the thing here. And for this to work, we will pass these two things onto our nodes, add that as a piece of information of the nodes in the graph. So this become a little bit too cluttered, so I guess I'll just clean it up a little bit. And the substring is just the zeros filled in this candidate tuple, and I'm just gonna unpack it here. Let me get rid of the old version. So if you want to look at the progress, you can pull back the timeline, I guess. So that's pretty much the code. Oh yeah, there is one more usage of this L and R here. That's in the determination of the valid candidate. We know when we are at the exact level. That's when the remaining L and R, the opening and closing parentheses we need to get rid of, is sum up to 0. So they are exactly 0 at the same time. So we can modify this condition here. So if we are not at the level yet, we actually don't go one pass through the string to check the validity. So that could potentially be some kind of time saving. So let's quickly check if we have problems. Yeah, this looks right. So let's try to submit this. Okay. Jeez. So let's try to run through example and submit. Okay, it's working. Again, I think the test set in the Leetcode website is not too big. So even though I think there should be some benefits in doing this, it's not obvious here. Note that the space here, it's always really bad here and not really good here, because that for the level-wise traversal, you can imagine that it's exponential in terms of number of possible nodes. In the worst case, for each level that you go further, and so since that now it's a deck here, it's just change one line of code. We can change this to DFS. And this will save some space, at least in theory. Let's see if it works. No. Why? I see. The reason is that for depth first search, once we find a result, it's actually exited. So for this to work, to become a depth first search, what we can do is this. We test whether the candidate is empty or not. Yeah. And we actually don't need this this loop anymore. Let's see if this works. Jeez. Yeah, I guess one thing we can do is should be a set here, and the condition here, it seems we shouldn't be testing this. Yeah, the reason that we missing one here is that the original testing logic is wrong. If it's a valid, we just append it there. Otherwise, we would try to extend this candidates here, and the prevention of us going to the next level is actually done by here. All right. So if both L and R are 0, it will never. I think it will never do this unless it's a constant character, which will be appending to the right or. Yeah, I think so. Let me grab this test case. Yeah, I think it will work. So, how are we doing on space? Not good. But this is I think it's indeed DFS. So if you think about the tree that's fanning out, you will follow one branch and only branch over there, and go branch even further until the minimum length, and then go backtrack. So I think it will be n squared of the total nodes. That's maximum in this stack. Where there's in the BFS version, it will be you will be exponential potentially. So yeah, so that's pretty much my solution. I'm avoiding the time and space complexity in accurate in detailed numbers, because I'm not I'm not 100% sure about my analysis. So I think I need more to grab some combinatory books, analysis algorithm books, to help me to reasoning through this more in more detail. But I think it's in the exponential territory, and for the space, it's in the quadratic space. If we do DFS, if we do BFS, that could be in the exponential territory again. And I guess the if you go DFS in the first trial, I think it's okay, but it's not that straightforward, as at least to me. It's not that natural. I think to have a BFS version, even a naive version that just brute force through all the branches as the first trial, and to try to look into the possible situations of the edges between those nodes. What are you double counting when you are double counting, and what are the parallel edges? How you from using a set to do explicit deduplication to make sure that the generation, the traversal, does not follow the parallel links. It's a good progress at least. So that's the question for today. It's getting too long and not quality anymore.